Hey everyone, so we're carrying on with section 7-2. I think in the last video I said 6-2, but that's wrong. So we're estimating mu, and right now we're doing the case confidence interval when sigma x is unknown, right? This is the realistic case. And this is going to require a new ingredient, which is called the t-distribution. So let's go back to the question of girls' birth weights. So suppose we're trying to estimate the mean birth weight mu x for all girls, and we don't know mu x and we don't know sigma x. Now, there's an Excel file there's a data set that we have that has the birth weights for a random sample of 205 girls. So later, we're going to calculate the x bar and s from the data set, but we don't need it quite yet. So for the moment, let's consider the distribution of x bar. Okay, so even though we don't know these parameters, it's still true that x bar follows a distribution with mu x bar is mu x, which is unknown. Sigma x bar is sigma x over the square root of n. It's also unknown. Furthermore, the distribution of x bar is normal as long as one of the following conditions holds. This is the central limit theorem. So as long as x is normal, which we don't know, or maybe it is, maybe it isn't, or the sample size is large enough, typically we say greater than or equal to 30. Okay, now contrary to what we just did in the last video, there's no point forming the standard test statistic Z because we don't know this sigma x. Okay, so what we do instead, what do we know? What we do is instead of using sigma x, we're going to use s in the same place. So that's called t. We'll calculate the t statistic, which is x bar minus the mean. S, so instead of sigma, it's s divided by the square root of n. And the difference here is that we know s from the sample data. We still don't know this mean here, but it'll turn out, but that's going to be okay. That will be okay. Okay, you'll see in a minute. Okay, so now what's the difference? Now, since s is approximately equal to sigma x, right? The sample standard deviation is not wildly different. It's similar to sigma x. The possible values of t are distributed similarly to the values of z, a standard normal. However, since s tends to be smaller than sigma, the statistic t has a different shape. It's a bit more spread out. And it has a name. It's called the t-distribution or the student t-distribution. Now, student t-distribution is a strange name, but actually it's because student is a kind of anonymous name. So the guy who developed this was working at a private company where they weren't allowed to publish research, and so he published it anonymously under the name student. So he was a student of statistics, I guess. Now, so what's the difference? The t-distribution is like this blue one here. So it's a little bit shorter and wider, right? It takes longer to flatten out than the green one, shorter and wider than a standard normal. A little bit more spread. The other thing to notice is that, so I should point out, the green one is the standard normal. So it's taller and skinnier. Now, there's another complication here, which is that the t distribution depends on n, changes depending on n. So if we have if we have a small n makes it shorter and wider, and a large n makes it taller and narrower. And if you have a really large n, so as n for a very large n, I have some sounds of the family in the other room. Hopefully you can't hear it. For a very large n, then it actually becomes the same as a normal distribution. So if you have a very large sample size, this strange new thing, the t distribution, is just the same as what we're used to, the standard normal. Okay, now I said a couple of these things already. The shape of the student t distribution depends slightly on the size of the sample n. For reasons that are not very important for us, we say that the shape of the t distribution is determined by this number df n minus 1. And df stands for degrees of freedom. And we don't need to worry about why that's called that right now. It's just, instead of saying that it depends on n, we say that it depends on the degrees of freedom, which is n minus 1. No big deal. So to form, here's how we actually do the confidence interval. To form a confidence interval at the level 1 minus alpha, we first calculate a critical t statistic. Critical t statistic. It's like what we did before with the z statistic, but we're going to call this t alpha over 2. And then down here is negative t alpha over 2. This area is 1 minus alpha. This area is alpha over 2. This area is also alpha over 2. And how do we calculate it? Let's say we had 5% alpha. So in other words, 1 minus alpha would be 95%. We would get, here's how we calculate it. T alpha over 2 would be t 0.025. How do we get it? We're going to use Excel again. But now instead of being norm.s.inverse, it's t dot inverse. I can use capital letters. T dot inverse. And we have to tell it the area, which is 1 minus alpha over 2. But we also have to tell it the degrees of freedom, which is n minus 1. So because the shape depends on n, it can't figure out the critical t value unless it knows the n. So this is the general way that you'll do it. So let's see. I guess I was going to do it. So let me actually do the calculation here. I'm kind of mixing a specific case with a general case here. Let me do it on the next line here. Okay, we do know the n side. We do know the n, right? So the n is 205. So this is going to be 1 minus 0.025. And this is going to be 205 minus 1, 204. So let's see, what does Excel tell us? So equals t dot inv. Probability is 1 minus 0.025. The degrees of freedom is 205 minus 1, which is 204. Bang. 1.97166. 1.97166. 166. So notice that if it was Z, we know that we've done it enough times that we know that for 95% confidence, the critical Z is 1.96. Here it's a bit larger, 1.97, and that's because the t distribution is a bit wider, a little bit wider. Okay, how do we proceed here? For 95% of all samples of size 205, we know that t is between negative t alpha over 2, which is negative 1.97166, and t, the positive version, t alpha over 2, which is positive 1.97166. Now, so what? This implies that what was the t statistic even? Where did it come from? It came from standardizing the sample mean, which was this. This was the t statistic. So that's between the positive critical value and the negative critical value. Great. Now, we're going to manipulate this until it becomes an interval for mu x. We're going to change that around until it's a left side and a right side for mu x. So what should we do first then? What you would do is multiply everything through by s over square root of n. So we would get negative t alpha over 2 s over square root of n less than or equal to mu x plus, sorry, it's been a long day, sigma, I'm just making random sounds now, x bar minus mu x s over square root of n. Now what? How do I get the x bar out of there? I can subtract x bar from everything, and that will get rid of that. And then the last step, if I multiply everything by minus 1, then I end up with my final answer. This will become x bar plus t alpha over 2 s over square root of n. This is x bar minus. And just like with p hat, we call this the margin of error. This is the margin of error. Okay, so that's the general pattern, and we got there a little more quickly than in the previous section because you're a bit used to it now. So from this data set, we can actually calculate the mean and the S. So let's actually go there. I'm going to just pause for a moment while I get the data set up. Okay, and so the data set, this file 4-births looks like the following. So it has many columns here. Most of these don't matter. These are information like the hospital, how long did the mother stay in the hospital, so on. What we care about is the birth weight here and the gender. So we just want the girls. So what we're going to do is select all these columns and sort it by gender. So how do you sort? You go to Data, Sort. Here we need to use the Sort dialog box because it's a complicated one. So, well, not complicated, but we need to sort by a specific column. We want to sort it by gender, which is this one, gender. And this one is checked, that's correct. My data has headers, which is right. It has those labels at the top. Okay, so now all the girls are listed first here. 0 is female, 1 is male. And the females stop here at row 206. Row 206. So where are the weights? The weights are here. So these are the weights from this column from row 2 to row 206. That's why there's 205. So let's say the X bar value is going to be average of G2 up to G206, right? G2 to G206. And the S, the sample standard deviation, is stdev.s G2 to G206. Those are my sample statistics. So what are we going to do with those? We'll just copy them back into our notes here. So X bar was 3037, 3037. What are the units on this? 3037.0732. The units here are grams. They measure the child in grams. Right? It seems a little funny, like we're measuring, I don't know, bulk food or something. But and S is 706 grams, 706.268 grams. Okay, so what is the 95% confidence interval for the mean mu? Well, we know that mu x is between the sample mean plus, what was the critical t-value? It was 1.97166. That's from up here. And S is 706.268 divided by the square root of n, which is 205. Now this, I'm going to do this side first fully because this is what we call E, this margin of error, and it'll save me a little bit of writing on that side. So what is that? Mu x is less than or equal to 3037.0732 plus, I'm going to just use Excel for this calculation. So E is going to be the critical Z value, which is, why don't I just calculate it again? T dot inverse of 1 minus 0.025. Degrees of freedom was 204. That's my T, times S is cell K3 divided by square root of n, 205. There we go. There's my margin of error, 97.26. Let's call it 97.26 grams. So that means on this side, it's going to be X bar minus T alpha over 2 S over square root of n, which I can just call minus E. So I know what that is now. Minus 97.26. So what's my final answer here? Here I'll say X bar plus E is K2 plus K5. X bar minus E is K2 minus K5. So there's my upper and lower limits. The lower one, 2939.8. So the rule of thumb here is how many digits should we keep? We should, if we're given the data like this, we should keep one extra significant digit. So all of these measurements have either, they generally have two, right? They're something, something, 0, 0. So we'll state our answer with one extra digit of precision. So we'll have 3 digits. So it'll be 2940, 294. Well, let's write out the number and then I'll round it. 0.8152 up to 3134.33. And we're going to round these to 3 digits here, because the original data had 2 significant figures. So 3130 grams, 2940 grams. So that's our 95% confidence interval. 95% confident that, based on that sample, the true population mean is between these two numbers. Okay, so let's see where we're at. That's enough for this one video, so let's stop there.